I would now invite Craig Walton from the University of Cambridge to get ready for his talk.
Hi everyone, I'm really excited to be here today presenting some work from my PhD, which I actually just handed in a few weeks ago. The main idea I want to convey to you today is that we may be able to use meteorites to test ideas about the dynamical evolution of our solar system, in particular focusing on novel archives of moon formation. The formation of the moon in a cataclysmic collision is challenging to reconstruct in detail. Different models make different predictions about the dynamics of this event, the speed, the angle of the collision, and the timing. This is interesting as we may be able to test those different models using archives of moon formation. For example, I'm quite interested in the debris from moon formation, which may have been flung out into the solar system and gone on to collide with asteroids. These secondary collisions may have written a record of moon formation into rocks throughout the solar system. Indeed, uranium-lead phosphate ages for shocked meteorites cluster around when most models independently suggest that moon formation may have occurred. Uranium-lead ages date thermal histories, the last time that the phosphate grains from which they are measured cooled down below a certain temperature. The striking age cluster around 4,450 million years ago to slightly older may indicate, therefore, that the asteroid belt was heated up by a dramatic pulse of collisions at this time, after the end of parent body radiogenic metamorphism around the time of moon formation. However, there are several pretty big caveats to this interpretation. Firstly, we need to actually understand what these old uranium-lead ages from shocked meteorites really mean. We need to know if they're dating anything real or just artifacts. We need to know whether or not our sampling of the asteroid belt is in any way appropriate for making such big interpretations of the sparse data. And we need to be sure whether or not there are any other dynamical events occurring around the same time, which actually would complicate what we expect the uranium-lead age record of asteroids to look like. But before we get to answering any of those fairly granular questions, I'd like to step back first and ask, why exactly are we choosing to focus on something other than the moon and the Earth in order to understand Earth-moon formation? So craters evidence collisions, and we certainly find craters on planetary surfaces. However, planets to some extent are kind of bad at recording collisional activity from the earlier solar system. At least in their youth, rocky planets are active worlds. In the case of Earth and Mars, having rivers and mountain building and volcanism, which erases the evidence for early collisions by continuous resurfacing. But primitive asteroids have very long memories. At least after the first few tens of million years of solar system history, as asteroids become nice and cold, there is essentially nothing happening to an asteroid except for collisions. So all in all, we have a situation where rocks from the deep past of planets, where the most dramatic collisional events may have occurred, preserve something like a faded painting, rather than the detailed and pristine original. And meteorites from asteroids may offer a more reliable archive of early solar system history. But that is also tricky in its own right, because we only have fragmented pieces of asteroids to work with in the form of our meteorite samples. Perhaps the most useful phosphate mineral in meteorites for investigating this problem is apatite, calcium phosphate mineral, which is ubiquitous in many samples and can be used to obtain uranium-lead ages. Uranium is compatible in the apatite crystal structure, whereas lead is not, which allows us to assume during a measurement that all of the lead we find has been generated by radioactive uranium decay, for which the relevant half-lives are known. An estimate can therefore be obtained of how long the mineral grain has spent below the closure temperature for lead diffusion, above which that temperature, the radiogenic clock for the mineral would remain perpetually at zero. If a grain has remained a closed system since it first formed, we will obtain what is called a concordant data point, lying on the Concordia line. The Concordia line is the solution to the age equations of uranium decay. A closed system grain will move smoothly along this line to the point that we observe at whatever time we're measuring that grain in a mass spectrometer. But nature is fickle. Our wonderful closed system may be subject to an episode of high temperatures, such as a collision. In this case, lead will begin to escape from the crystal and our isotope compositions will evolve, moving along a straight line towards the origin. Data points lying in this region of the graph are called discordant. Because diffusion rates from crystals will vary depending on the local temperatures reached or their grain size, the degree of lead loss, or discordance, will vary. By plotting a linear regression through the newly scattered compositions, we can recover information. The upper intercept of the regression with the Concordia age curve reflects the time at which lead was last zero within the grains. possibly the time of formation, or some earlier high temperature event that flushed the system of lead completely. The lower intercept of the discordant data regression line with the Concordia line reveals the time at which lead loss most recently took place. In this way, we can see how extremely different ages may be recovered by a single suite of phosphates, which may reasonably span even the 4.5 billion years of solar system history witnessed by asteroids. But picking apart these ages and what they mean is pretty controversial. For example, take the Chelyabinsk meteorite, which has been a key sample in my project. Chelyabinsk is a highly shocked LL5 type ordinary chondrite meteorite, which preserves three distinct lithologies. It has a light lithology, which is the least shocked, essentially representing the original host rock of the parental asteroid. You have a dark lithology, where metal and sulfide veins have penetrated into the silicates and produced an optically dark texture. And you have the melt lithology, which is exactly what it says in the tin. It's shock melt produced during a violent collision. Previous work shows that all of these lithologies formed from the same parental material at the same time. Each lithology reached different peak temperatures before thermally equilibrating with one another, but they failed to texturally equilibrate. And hugely different ages have been obtained for potential impact events affecting Chelyabinsk using the phosphate uranium lead system. And both of these wildly disparate ages have been related to the formation of the light-dark melt structure of the meteorite. Clearly, we need to try and resolve this. We need to know at what time Chelyabinsk experienced the most dramatic collisional heating, for which its textures provide some evidence. We need to know whether or not the upper intercept of the data that's been measured actually reflects any sort of collision at all. This is quite important, given that the upper intercept age for Chelyabinsk is part of that possible moon formation-related cluster I mentioned at the start. Our idea to distinguish between the lower intercept and upper intercept ages as reflecting a major collision was to see if there was any systematic variation in the measured uranium-lead compositions between the differently shocked lithologies of Chelyabinsk, and indeed when comparing between variably deformed grains within individual lithologies. We can essentially construct two competing hypotheses for the interpretation of the data. Option one, if recent lead loss occurred during the formation of the light-dark melt lithologies, we would expect a correlation between lithology and lead loss. Dark lithology grains will have reached higher temperatures for longer and should have lost more lead. That is, we will observe a macro-scale correlation between lead loss and phosphate setting in the meteorite. The second option is that if recent lead loss occurred during a more minor recent event, and the three lithologies actually formed a very long time ago, there should be no such correlation of lead loss with lithology. We may instead expect lead loss to correlate within each lithology with overprinting textural features, such as fractures, which could have damaged the phosphate crystal lattice and enabled lead loss at low temperature. And we tested these scenarios by applying secondary ionization mass spectrometry analysis to the phosphates in Chelyabinsk, which give us spatially resolved compositions that we can relate to independent observations of the mineral textures. And the microtextures of phosphates in these meteorites could really be entirely different talks in their own right, but suffice to say that we can identify two major classes. We looked at the grains using electron backscatter diffraction, or EBSD analysis, which allows you to work out whether or not a crystal lattice is oriented as one would expect for a single grain, or if it's best represented as a strained lattice, or perhaps lots of individually smaller, unstrained, but randomly oriented grains. And we observe crystoplastic deformation of individual crystals, where strain has been accommodated during a collision over numerous stacked slip planes in the light lithology. And in contrast, in the dark lithology, we find phosphates which have been recrystallized. Here, strain is absent. Parental grains have been reorganized into individually smaller grains with clear boundaries and essentially random orientations. This tends to take a long time, but could be sped up at high temperature. And because we only find such textures in the dark lithology, we can be quite confident that the higher temperatures required to produce that lithology have had a real consequence for the phosphate grains therein. And this provides a nice setup verifying the reasonableness of the macroscale correlation we might expect if the thermal event happened recently. The phosphates in the dark lithology definitely reached higher temperatures, and it had a real crystallographic outcome for them. But overprinting those high temperature textures are fractures. We find crystal domains with defects such as these, which may be more susceptible to lead loss at lower temperatures. But fractured domains are often avoided during uranium-lead analyses in favor of pristine areas, which misses a crucial point. What if the uranium-lead discordance observed in Chelyabinsk and many other meteoritic phosphates is simply derived from catching damaged domains in your placement of spots, despite people's best efforts to avoid them? We should analyze them intentionally and see whether we find more extreme results. And the widespread presence of these fractures in Chelyabinsk, which overprint the high temperature related features I just showed you, provide a reasonable basis for the second hypothesis, that a microscale correlation of uranium-lead discordance with fractures might imply an ancient major impact, followed by a more recent event that induced discordance. And now we get to the actual results of the analysis, where we can find out which of these options makes the most sense. So once again, you're looking at spot data plotted on Concordia diagrams. The light blue markers indicate the center of ellipsoidal errors. I have plotted previously measured data from one of those earlier studies on Chelyabinsk with brown triangle markers. On the left-hand plot, the data are color-coded by lithology, purple for dark lithology, orange for light lithology. On the right-hand plot, the data are color-coded by crystal domain. Light purple are damaged, where the spots overlap fractures, and red is pristine, where there was no visible defects in the proximity of the analysis. Below each plot are graphs of the cumulative distribution of the 207 lead 235 uranium compositions, allowing us to visualize how similar these data groupings are. I've shaded in green a reasonable range of graph space that corresponds, given our errors, to concordant data. And there are several really key observations to make from the data. The first is that our data define a much wider range of compositions than the previous studies, falling well along the regression line and almost reaching the lower intercept itself. That is to say, we observe grains with much more extensive lead loss than previous studies. That's a pretty important finding, and it came from the fact that we intentionally analyzed highly fractured grains. For one, it allows us to much more tightly constrain that lower intercept age. We are no longer extrapolating miles away from where we have the most data to calculate our lower intercept. We also clearly see that discordance in Chelyabinsk is mainly related to those fractures. What all of that comes down to is a rejection of the first hypothesis I posed. There is no macroscale correlation of lithology with phosphate uranium lead ages. The light and the dark lithology are essentially identical for this perspective. Meanwhile, there is a strong correlation between damage-related microtextures, such as fractures, and the uranium-lead isotope composition of the phosphate minerals. We can therefore infer that the plastic deformation and the recrystallization of the phosphates, and overall the major collision that created the light-dark melt macrotexture of Chelyabinsk, occurred at the time indicated by the upper intercept, or 4.47 billion years ago, coincident with when moon formation may have happened. Late lead loss then took place during a much more recent event that overprinted those high energy textures with fractures. And the best estimate we can get for that by putting all the data together is actually within error of the present day, suggesting that that may simply reflect the splitting of Chelyabinsk off from its parent asteroid and being hurtled towards the Earth. And now for the final slide, I want to go back to the big picture and ask, with our new confidence in what meteorite phosphate uranium lead ages actually mean, do we bolster or diminish the idea of tracing dynamical events with meteorites? From my data, I would say we can have renewed confidence that upper intercept ages younger than the end of parent body heating on asteroids do reliably record intense collisional reheating, or at least they do in Chelyabinsk. And the clustering of ages from 4450 to 4480 million years ago in meteorites from various different parent bodies is plausibly indicative of a major dynamical event at this time. That could be moon formation. It could also be something else. For example, there are different astronomical models for a late instability at this time related to the migration of the giant planets. This may have dynamically excited the asteroid belt and produced a similar signal. So there's a lot of work to be done there in actually getting the astronomers on side to make really specific predictions for the consequences of a process for exciting the asteroid belt. That goes both for moon formation and competing ideas. So much work remains to be done, measuring more ages, because this is a fairly sparse data set still, looking at different meteorite types, increasing the statistical power of the number of ages we have, improving the models to make predictions for uranium lead ages from the dynamics. And that's the sort of stuff that I'm looking to do in the future. I was in Sweden last week at the NordSim facility measuring loads more ages, which I'll have to process and see if they back up the idea of a major event at this time or not. But all that being said, I think the results from shell events do set the stage for being able to interpret the collisional history of individual meteorites more easily, which in turn makes it easier to try and construct the collisional history of the solar system with shock meteorites in general. And that's it. So any questions? Love to hear them, or any ideas. Thanks.
That's my speaker. Thank you very much, Craig. We do have 2 questions in the chat, but we are also 5 minutes behind. One from Josh Snape and one from Roman. Josh is asking if regarding your discordance of your data, if any of the grades could be meteorite, for example.
Yeah, that's good. Should I answer them in the chat?
Just quickly and then get to the chat.
We did distinguish between apatite and meteorite, both with EDS and the EBSD. I just didn't go into that. But sometimes the grains are intergrown, so it could be quite difficult to like make sure you're not on them. But that's a good point, actually. The reverse discordance is a bit unusual. I don't think it's just from analyzing meteorite. Could be during the formation of the fractures and the formation of the discordant grains, you end up with the opposite in what's left behind. If you guys have thought more about that, I'd love to hear your ideas.
Thank you, Craig. We will now move to the next speaker.
Okay, thank you.